Our next speaker of the evening was appointed the Patterson Rockwood Professor of Energy in Harvard's Department of Chemistry and Chemical Biology. His newest invention, the artificial leaf, which converts sunlight and water into a chemical fuel that can be stored and used later, makes the shakeable flashlight look more foolish than a shake weight, which also outperformed the ShamWow with 4 stars on Amazon. I checked that one backstage. He, too, is a member of both the American Academy of Arts and Sciences and the National Academy of Sciences. Please give a warm welcome to Professor Daniel Nocera.
Thank you, sir. So I'll end tonight, and I would like to just ask a small thing of Harvard students. Will you help me start a new epoch in humankind? It's a small thing. And I call it the Sustainocene. And to put it into perspective, you should think about epochs. And so here's our latest ones. You have the Holocene. That's around 10,000 years ago, and that's when there wasn't enough of you to mess up the Earth. Right? It's because there just weren't a lot of us, so human activity didn't affect the planet. And then around 1800, you may have heard this word, Anthropocene, and that's where there's enough of us now that our human activities start putting the planet out of balance. And you heard some of that tonight from Professor Schrag and Anderson. What's the Sustainocene? I'm calling it a new epoch. That actually was a term coined by an Australian physician earlier this year. And this part you're probably familiar with if you hear sustainability, ecological sustainability, environmental integrity. But that's not enough as we move forward. All right? That has the planet only as part of the equation. But there's another piece of this, and that's you, humanity. And the Sustainocene goes one step further beyond the planet, and it looks at eliminating gross societal imbalances and poverty. That's also a world out of balance, the haves and the have-nots. And I'm here to tell you tonight, the haves, I don't care about anymore. Because, oh my God, this is Harvard. Communist Cambridge is at its fullest tonight, thank God. Usually I get heckling in Washington. But it's because you guys aren't going to make a difference. It's all these silent voices that we don't hear anymore. And you're going to have to get them in balance with us. And that's what the Sustainocene seeks to do. And it's to do that by looking at the energy, food, and water problem. Tonight, I'm an energy guy. So I'm going to start off with energy, and the reason is that's the place to start, because if you get that right, you can do food and you can do water. Right? So tonight I'm going to talk about the Sustainocene, and I'm going to start as an entry and portal into this problem is energy. Now, the one thing, I'm coming here from MIT, you heard why. Because I read all of Jim Anderson's papers, and I'm a terrible swimmer. So I'm only coming to Harvard for one reason, higher ground. That's it, okay? But when I get here, we're not going to have any more talk about how you feel about energy or how you feel about stuff. I don't care about how you feel anymore. We're going to be really analytical, and we're going to calculate stuff, and it's going to be no arguments. It's all right? So here's how you use energy. So how do you use energy? I'm telling you, that's the formula for using energy. There's how many of you are there in the world, population, that's here, GDP per capita, how rich a country is per person, so if I know that, and then this is the formula for conservation. Conservation isn't necessarily a feeling, something you do. It's can I grow an economy, maintain my GDP, and use less energy? That's the formula for conservation. When you multiply all that together, population times GDP per N times eGDP, you get the amount of energy used. So you don't have to feel anything about energy anymore. If I know the population and I know the gross domestic product for every country and I sum over all those and then I take the energy intensity, that's what that's called, I can calculate energy. So in 2012, I can calculate your energy. Good scientists and engineers know that's not an energy, that's a power, terawatt, it's a watt. So how much energy do I need to burn the light bulb? Right now, you are burning a 16 trillion watt light bulb, right now as I'm speaking. So that's not how much energy I'm using, it's energy per unit time. How much energy do I need to keep the light bulb lit? And you out there, the world, is burning 16 terawatts. I can use my formula and then calculate how much energy you're going to need now and in the future. So close your eyes or just think right now, 2050. So add 38 years to your life or somebody you know, a young person. You're old already, you don't know it. And Harvard's going to make you older before you leave, believe me. So you're going to need 30 terawatts in 2050. You're going to just basically double your energy need. By the end of the century, triple it, all right, if you do the formula. You can find energy everywhere. I like all of these. They're all carbon neutral. But again, let's be analytical. So I always hear people get all hot and bothered by nuclear. I don't even want to get into the argument. Let's just do the calculation. I need around 16 more terawatts. So say I got 8 terawatts from nuclear. I can do the math. A nuclear power plant, how much do you build it at? A gigawatt. You don't like making them bigger because they get dangerous. So if I take 8 terawatts and divide it by a gigawatt, what's the number? 8,000. So if I want 8 terawatts of nuclear energy, you're going to have to build me 8,000 new nuclear power plants. And I said in 40 years I need that energy, so let's keep doing the math. 8,000 divided by 40, 200. There's 365 days in a year. So you got to build me a new nuclear power plant every 1.5 days to get to 8 terawatts. You better really like nuclear, because you're going to be building a lot of it. And I said forever. Why would I say forever? Because when I build a nuclear power plant, I need to decommission it after 50 years or it's dangerous. So the one you just finished in 1.5 days, just as you're done building it, get ready to decommission the one you started with, because I got to rebuild it to maintain my 8 terawatts. Okay? So if you like nuclear, that's what you're in for. I can go through these other numbers, and it's all calculus, analytical stuff. I'm not making a political statement. This is doing the numbers, all right? Plant biomass on the entire face of the earth with the fastest growing crops. You get 6 terawatts. All right, that's it. So you start thinking, this isn't a big deal, 16 to 30. Look at these numbers. This is total amounts of energy. I'm a solar guy. Why do I like solar? Because there's a lot of it. Okay? You can get your hands on it. Let's start breaking the numbers down then. If there's 16 terawatts, I'm going to need 16. I need 16 more. Let's keep being analytical. One thing I forgot to tell you in my calculation to 30, I made the assumption that you're going to save 14 terawatts by 2050. That's energy intensity. So in my calculation, I assumed you're going to be good human beings, have great science and technology, and save 14 terawatts. And I still need 16 terawatts more. So why is that the case? Now I get to my original has nothing to do with you. There's 3 billion people who aren't born yet. They're coming by 2050. And there's 3 billion of you who you don't hear or see, mostly the poor, and they don't use hardly any energy. So when you take those 6 billion people, and then I assign them an energy unit, and by the way, in case you've never realized it, if you calculate how many calories you're using a day, you're all 100-watt light bulbs. And so you really do shine brightly to me tonight, right? But isn't that sweet? She said, ah. Okay. So there's 6 billion, we need 6 billion new energy users, and if you start assigning 100 watts to them and do the math, that starts adding up. But there's a more important thing. It's not that they're going to take all the 16 terawatts, but as they increase in their needs, you want to set them off on the right path. And you've chosen the wrong one, coal, oil, and gas. And so if you want to get these people off on the right path and then have the right trajectory, you've got to start now with them. And that means you've got to do science and engineering in a different way. Jim and I are in the Academy of Sciences. Woo-hoo. You know how you get there? I have the brightest and shiniest and best thing in the world. Guess what? Who cares? When you're poor, you want the cheapest thing. You don't have anything, right? So it means in the next century, we're going to have to do science in a different way. I call it not the est science, the biggest, the smallest, the fastest, the slowest. That's what we do as scientists. It's doing science in a different way for the poor. And the beauty of that, if you address this problem, you actually go to the mission statement of the Sustainocene, to bring life into balance, just not ecologically, but humankind too. So that's why I would like to start this journey here at Harvard. Now, I just want to tell you quickly, just to end, I heard a lot about cities tonight. I just assigned an energy value to all of you, and then I said I did math. I did arithmetic, as Bill Clinton said. What did I do? I assigned energy to you. I said there'll be 9.2 billion, and then I did multiplication. I extrapolated. I'm not the first to do that. My friend Bill Toomas got me onto this. In 1898, the first civil engineering conference gathered in New York City, and they didn't talk about land development or economic infrastructure. They were driven to desperation by horse manure. The situation seemed dire. So what did they do? They said, here are poor people. Here are poor people. They don't own a horse. Here are rich people. They own horses. I know how much doo-doo comes out of a horse. I'll weigh it. And then by 1950, these people are going to become rich. They're going to own horses. And now I got to just look at how much doo-doo comes out of a horse. And oh my God, in Times of London said by 1950, every street would be 9 feet deep in horse manure. So forget about all the city planning. This is where the rubber hits the road, okay? By 1930, horse manure would rise to the 3rd story of every Manhattan building. And no possible solution could be devised. And that's because by the time, look at what time, 1898, the internal combustion engine was already developed. Like Dan said, there was something happening. It's not working out so well right now. Like it saved the whales. You saved yourself being 9 feet deep in horse, okay? So that's pretty good. But people didn't see that. That's what scientists do. We can, because that's extrapolation. When we invent something, you get on a different curve. The math doesn't add up. And that's what is called a paradigm shift. It's a change in how things are done, and all of a sudden the old math doesn't apply. So that is a good demonstration of paradigm shift, and it also proves to you that shift happens. I worked hard for that one, Cashin. Get them going here for me, please. So, Jack Cashin, what are you, a junior or senior now? Senior. Oh, God. Okay, wait until the world gets a hold of Cashin. All right, so shift happens. So let me tell you a little bit of shift going on right now. This is how photosynthesis works. I don't know if you've ever thought about it. You remember in grade school, sunlight plus water plus CO2 makes sugar and O2. What they didn't tell you in grade school is sunlight comes in, the first thing the plant does is it splits water to oxygen and hydrogen. The hydrogen's then stored with CO2 to make sugar, but there's no energy storage here, none. That's just a way to store hydrogen because it's a gas. So it's all the energy storage is in water splitting. So what do I mean by that? Here's gasoline, carbon, 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 hydrogen. I'm a chemist. You're going to learn this now. I'm sorry. I'm in front of students. You're going to learn some chemistry. There's oxygen, oxygen. Watch, I'm going to burn the fuel. You see that? First thing is you should watch. That's 14 hours of PowerPoint right there. Okay, so I took high energy bonds, I burned it, got low energy bonds, and then what do I get out of it? Energy. What does photosynthesis do? Takes low energy content bonds in water, uses the plant, and then splits it to make hydrogen and oxygen. And then you burn the hydrogen. You can do it in a fuel cell, you could burn it, you could fix H2 with CO2, make a liquid fuel. That's what photosynthesis does. Why did it do that? This is how much energy is in water. If you take thermo from Professor Anderson, he's going to teach you that. I can then calculate that in a liter of water, I could store 13 megajoules of energy if I rearrange the bonds of water. That's the Harvard swimming pool. The hardest number was to get how many liters are in there, so I did. And now I can calculate how much energy I could store in that swimming pool. So, but I'm going to put it in power, because I told you I need 16 terawatts. What happens if I take water and convert it to hydrogen and oxygen per second? How much energy could I store? Remember how hard it was to get 8 terawatts? So if I could take a swimming pool of water globally per second to hydrogen and oxygen using the sun, look at the number, 38 terawatts. You only need 16. So you give me a pool of water, and if I could build a little energy device that I put in water, takes the sunlight, and then acts on the water and makes hydrogen and oxygen per second, you're at that amount of energy, okay? And so what I'll do, oh, I see, I didn't tell you 38 terawatts. That's what Dan was telling me. Dan Schrag's going there, advance the clicker, advance the clicker. And I started rushing, because I don't want to be out of time either. So that's how much energy you can save. Isn't that beautiful? I can solve this world's energy problem carbon neutral just using sunlight in a pool of water. Are you going to use up the water per second? Nope, because what happens when you recombine hydrogen and oxygen? Energy comes out, you burn it, and you get the water back. So it's a closed cycle with the only input, sun in, energy out. So that's really beautiful. That's a tough job. People have been saying, can you do photosynthesis since 1912? Emulate what plants do. That would be nice for life. So a lot of people have tried. I'll just show you, I told you I was going to tell you some shift happening. We took some piece of silicon, and I'm not going to go into it. This isn't important. This is what job is of a scientist. But we figured out you could take sunlight, you then generate a wireless current, so like current out of a wall, we make a current. We made 2 special compounds that could capture the current, and then with that current, but no wires, and that's how a plant works. Sunlight comes in, wireless current, split water. Sunlight in, wireless current, split water. We made this thing, the artificial leaf. And if you see, there's no wires, just layers, no membranes, works in any water source, simple engineering, highly manufacturable. Why am I saying all that? Because I just want to show you. So there it is, no big engineering. We made like a McDonald's hamburger, it's just layers. Drop it in water. So you just have a thing in water, splitting hydrogen and oxygen. You just send it to poor people. So that's the beauty of it. It's simple to use. There are people, this is a friend of Harvard. He's a mentor of mine and friend of mine, but he's also a friend of this university, Mr. Tata. And he's been trying to tell people, get up in the morning and do stuff for poor people. And if you want to make money, he's even telling you do it. He runs a huge conglomerate, $160 billion conglomerate, taking care of the poor of India. So it can be done. Why Harvard to end in the Sustainocene? And it gets back to Dan Schrag. He was saying there's 3 views. The 3 views you can't separate them. It's multiplication. It's sociology and culture times economics and policy times science and innovation. I just told you that because I'm a science geek. But I can't get this thing adopted if I don't understand sociology and culture and policy and economics and everything you heard today. And why Harvard? It's the only university that does all 3 pieces of the equation. So I want you all to be scientists, but you don't have to be to solve this problem, and it's every school at Harvard, and they all have to work together. It's the only school, in my opinion, that holistically can treat the problem. And it's going to be up to you guys to do it. And you only have like 38 years. So with that, thanks for listening.